Okay, we'll start now. So is it visible?
Yes, sir.
Okay. So today we'll discuss about Raman spectroscopy. So another spectroscopic technique used in different chemical analysis. So Raman spectroscopy was discovered by famous Indian scientist C.V. Raman in 1928. It is a spectroscopic technique used to observe vibration, rotation, and other low frequency modes in a system. So, Raman spectroscopy is also commonly used in chemistry to provide fingerprints by which molecule can be identified. When the radiation passes through the transparent medium, the species present scattered a fraction of the beam in all directions. So when we are radiating a beam in a transparent medium, the species present will scatter and all the rays will scatter in different directions. So Raman scattering results from the same type of quantitative vibration change associated with IRC. The difference in wavelength in between the incident and scatter vibration radiation corresponds to wavelength in milli-IR. So when monochromatic radiation is incident upon a sample, then this light will interact with sample in some fashion. It may be reflected, it may absorb, it may scatter in some manner. So it is the scattering of radiation that occurs which gives information about the molecular structure. Raman is based on scattering light. So when a light will fall on a matter that can reflect, can absorb, can scatter. So in Raman spectroscopy, we will talk about scattering light. The sample is irradiated with a coherent source, typically a laser. Most of the radiation is elastically scattered. So that scattered light is known as relay scattering. A small portion is inelastically scattered. That is called Raman scatter, composed of Stokes and anti-Stokes portion. So this will be known as Stokes or anti-Stokes. This latter portion is what we are particularly interested in because it contains information in which we are interested. The spectrum is measured with a laser line as a reference, hence the peaks are measured as the shift from the laser. The peak position is determined by the vibrational energy associated with the bonds in the molecules which sample is composed. Because of this, spectrum ends up looking very similar to an iris is interpreted similar. There is a footnote to this, however, as the principle of mutual exclusion applies, that is the peaks that are emphasized in IR. So in IR, we should have a high dipole and de-emphasize somewhat in Raman. The bands that are emphasized in Raman spectrum are those that are due to highly polarized bands. So you can see These are the different lines observed in Raman spectrum: Stokes scattering, anti-Stokes scattering, Rayleigh scattering. So you can see here, we'll see Stokes peak, anti-Stokes peak here. So you can see anti-Stokes. So this Stokes from 0 to higher, and from anti-Stokes from high vibration energy, fast vibrational energy level to high. So listen, in case of Stokes, so we get energy H excited frequency minus original. But in case of anti-Stokes, we get H mu, that is frequency of excited plus frequency of vibration. So here one will be plus, another will be minus. So listen, these are the instrumentation of Raman scattering. So you have a laser source and another is a sample chamber, another is a wavelength selector, another is a radiation transmitter, and another is computer data system. So these are the instruments present in humans. So if you look at the different instrumentation parts, first we will discuss about the source. Instrumentation of modern Raman spectroscopy consists of laser source, emitting system, suitable spectrum source. The sources used in modern Raman spectrometry are nearly always a laser because there is high intensity necessary to produce Raman scattering of sufficient intensity to be measured with a reasonable signal to noise ratio. Because the intensity of Raman scattering varies as the fourth power of frequency, argon shifted ion source that emit in the blue-green region of the spectrum. So what are the laser light? So we'll use argon ion. So wavelength around 488 nanometer. If we use krypton ion, that is 530 nanometer. So we can use helium neon ion laser type and diode and etc. So these are the possible lasers we can use in the Raman spectroscopy. Sample illuminating system. So liquid sample, a major advantage of sample handling in Raman spectroscopy compared with infrared arrays because water is a weak Raman scatter but a strong absorber of infrared rays. The aqueous solution can be studied by Raman spectroscopy but not by infrared. This advantage is particularly important for biological and inorganic systems in studies dealing with water pollution. Solid samples. Raman spectra of solid samples are often accurate by filling a small cavity with a sample at top. It has been known to be found. Polymers can easily be examined directly with no sample treatment. Gas are normally contained in glass tube, 1 to 1 to centimeter in diameter, about 1 thickness. Gases can be sealed in a small capillary. Raman spectrometer were similar in design, used the same type of components as the classical ultraviolet visual dispersing instrument. Most employed double grating system to minimize the spurious radiation reaching the transducer cell, photomultipliers, or as a transducer. Now, Raman spectrometers being marketed are either Fourier transform instruments equipped with cooled germanium transducer multi-channel instrument based upon the charge coupled device. Difference. So, what is the difference between Raman and infrared spectroscopy? So, last class we have studied the infrared spectroscopy. So, in Raman spectroscopy, it is due to scattering of light by vibrating molecule. It is the result of absorption light by vibration. So, here, due to the scattering of light, infrared is due to the absorption of light. The vibration is Raman active if it causes change in polarity. So the molecule will remain active if it has change in polarity. But molecule will vibrationally active or IR active if there is change in dipole moment. Okay. In Raman, the molecule need not possess a permanent dipole moment. But in case of infrared spectroscopy, the vibration concern should have a change in dipole moment due to the vibration. Water can be used as a solvent in Raman spectroscopy, but water cannot be used for the sample preparation in the IR spectroscopy. Sample preparation is not very elaborate. It can be any step. So gas, liquid, solid, whatever state in the Raman spectroscopy. Sample preparation is elaborate. Gaseous sample can rarely be used. So, in infrared spectroscopy, the gaseous state sometimes that gives an indication of covalent character in the molecule. So, in Raman spectroscopy, we can take the information of covalent character of molecule. Gives the indication of ionic character in the molecule. Infrared. Cost instrumentation is very high, comparatively inexpensive. So Raman instrument is very high cost, but infrared has less cost than Raman spectroscopy. So these are the difference between Raman spectroscopy and infrared. So you can read out carefully. So Raman's due to the scattering, IR due to the absorption. So Raman, here we need polarizability of molecule in vibrational or IR spectroscopy. We need permanent dipole moment. So here molecule need not permanent dipole moment, need not possess a permanent dipole. Water is used as a solvent. Here the water cannot be. So, so in Raman spectrum, what we see, we see sunset. So this is a real spectrum. So typical Raman spectra plot of signal interval. So this is x-axis is the Raman set, y-axis is the signal intensity. So Raman set expressed in centimeter inverse means wave number. Another photon or energy. So this is the Raman spectrum. So what are the applications of Raman spectra? So Raman spectra can be used in inorganic species, determination or analysis of inorganic species. The Raman technique is often superior to infrared spectroscopy. for investing in organic systems because aqueous solution can be absorbed. But in infrared spectroscopy, we can't use the aqueous solution. In addition, the vibrational energy of metal ligand bonds are generally in the range of 100 to 700 centimeters. A region of infrared is experimentally difficult. So vibrational energy of metal ligand bonds are generally varies from 100 to 700 centimeters. So in case of infrared, it is difficult. These vibrations are frequently Raman active. However, delta mu values is ranges are readily observed. Raman studies are potentially useful source of information concerning the composition, structure, and stability of coordination components. So Raman studies are potentially very useful source of information concerning the composition, structure, and stability of coordination components. So Raman spectra also can be used in case of organic species. So let's say Raman spectra are similar to infrared spectra in that they have regions that are useful for functional group. So Raman spectra can be used like infrared spectroscopy for detection of functional groups. And the fingerprint region permit the identification of cells. Raman spectra yield more information about certain type of organic compound than do their infrared counterpart. Quantitative application. Raman spectra tend to be less cluttered with peaks than infrared spectra. As a consequence, peak overlap in mixture is less likely and quantitative measurement are simple. In addition, Raman sampling devices are not subject to attack by moisture and small amounts of water in a sample. Biological application of Raman spectroscopy. Raman spectroscopy has been applied widely for the study of biological systems. The advantages of this technique include the small, simple requirement, minimum sensitivity towards interference by water, spatially detailed, and the conformational environment sensor. So, if you use the biological application of Raman spectroscopy, that can be used in different environmental sensitivity and determination of biological compounds. So this is all about a small part of Raman spectrum. So we can recap here what is Raman spectroscopy. So Raman spectroscopy use the scatter light here. So Raman scattering, also you can see Raman scattering. So here we'll use two peaks. We can observe three peaks. One is the relay scattering, anti-Stokes and Stokes scattering. So you can see here Stokes, anti-Stokes and relay scattering. So instrumentation. So we have different arrangement in the Raman spectrophotometer. So this is the difference between Raman spectroscopy and infrared spectroscopy. So we can see the Raman spectrum here. So middle one is relay scattering, and here anti-Stokes, and here Stokes. So this is the complete spectrum of Raman. So the first one is the middle one, a reference peak that is relay scattering, and right side is anti-strokes, left side is strokes. So these are the application of Raman spectra can be used for detection of inorganic species. Also, Raman spectra can be used for organic species for different quantitative applications. Also, Raman spectra can be used in biological. So this is all about Raman spectroscopy. So we'll move to another section. So now we'll talk about colorimetry and cosmology. So this is another spectroscopic technique used. Fluorimetry. What is fluorimetry? It is a measurement of fluorescence intensity at a particular intensity. So we will measure the intensity of fluorescence at a particular wavelength with the help of filter fluorimeter or spectrophotometer. So phosphorimetry, a form of fluorimetry in which phosphorence of a sample is measured in a conjunction with a pulse source of radiation. So like fluorimetry, phosphorence of a sample can be measured. So this is known as phosphorometry. So what is photoluminescence? PA. Photoluminescence is the spontaneous emission of light from a matter under optical excitation. So we can see spontaneous emission of light from a particular material under optical excitation. So that is known as photoluminescence. So it is further divided into fluorescence and phosphorus. So what is fluorescence? When a beam of light is incident on certain substances, emit visible light or radiation. This phenomenon is class when beam of light is incident on a certain substance, emit the visible light or radiation. This phenomenon is called fluorescence. Substance showing this phenomena is called fluorescent substances. This phenomena of fluorescence instantaneous start emitting radiation immediately after the absorption and stop when incident light is gone. Fluorescent substance emit maximum radiation within 10 to the power minus 10 to 10 to the power minus 8 second of absorption. So this is also called delayed phosphorescence. Fluorescence. So fluorescence also known as delayed fluorescence because it gives radiation 10 to the power minus 10 to 10 minus 8 seconds. So the substance which showing this phenomenon is called as fluorescent substance. Then what is phosphorescence? When light is incident on a certain substance, They emit light continuously even after the light is cut off. So, fluorescence, it will emit light and it will stop when light is cut off. But phosphorescence, it will emit light continuously even after light is cut off. This is called phosphorescence. And some substances are called fluorescent substances. In the fluorescence process, the electron didn't change in spin direction, but under the appropriate condition, a spin flip can occur. The light emission process must wait until electron undergoes spin flip to revert back to the original. Phosphorescent substances emit maximum radiation within 10 to the power minus 4 to 20 seconds or longer. Phosphorescence and flows. The emission could proceed either from a singlet or triplet state. The emission could proceed only from a single state. Short-lived electrons in excited state of fluorescence. Longer lifetime of excited. So listen, if you look at the Jablonski diagram, you can understand what is phosphorescence. So we'll see the Jablonski diagram after some slides. So a large number of substances are known which can absorb UV and visible light. But these substances lose excess energy as heat through collision with neighboring atom or molecules. However, number of molecules important substances are now which lose only a part of this excess energy as heat and emit the remaining energy as electromagnetic radiation of wavelength of longer than that absorbed. So this process of emitting radiation is known as luminescence. So what is luminescence? Number of molecules, important substances are known which lose only part of excess energy as heat. I emit the remaining energy as electromagnetic radiation with the longer. So this process of emitting radiation is called luminescence. Fluorescence is the emission of visible light by a substance that has absorbed light of a different wavelength. Emit photon has a longer wavelength. Fluorescence is related to fluorescence in emitting a photon. However, a phosphorescence material doesn't immediately emit the radiation. As the excitation of molecule is due to absorption of photon, this type of luminescence are called photoluminescence. As the excitation of molecule is due to absorption of photon, this type of luminescence is called photoluminescence. So what is chemoluminescence? So you can say chemoluminescence. Chemoluminescence is another phenomenon that falls in the category of luminescence. This refers to the emission of radiation during a chemical reaction. However, in such cases, excited state is not a result of absorption of electromagnetic. The excitation of luminol is an alkaline solution, is an example of chemoluminescence. So, chemoluminescence is another phenomenon that falls in the category of luminescence. This refers to the emission of radiation during a chemical reaction. So, in such cases, excited state is not a result of absorption electromagnetic. The excited luminol is an alkaline solution, is an example of chemoluminescence. So you can see this is a Jablonski diagram. When a molecule is excited in presence of light, so this is ground state, and this is the singlet state. First singlet state is the second singlet state, and this singlet state, when a molecule will excited, electron will excited, this can be triplet state. So if it will relax from singlet to singlet, that is the internal conversion. If we will emit from singlet to triplet, that will be known as intersystem crushing. So if the electron will relax from triplet to singlet, this is known as phosphorescence. So if you singlet to ground state, first singlet S1 to S0 means the first singlet state to ground state. This is fluorescence. But if you to jump the electron or relax the electron from T1 to S0, that is known as phosphorescence. Okay, so this is the Javelinski diagram. So here this S0 ground state is non-radiating relaxation and intersystem crossing, fluorescence, vibrational relaxation, internal conversion, etc. So listen, so from singlet to singlet, known as internal conversion. So these are the relaxation from one state to another. So internal, suppose the singlet to triplet, this is intersystem crossing, and this is known as delayed phosphorus. Okay, excited triplet state, non-radiated relaxation. So phosphorescence is a non-radiated. So listen, you can see fluorescence from S1 to S2. So this is possible due to loss of energy. So phosphorence, this is fluorescence. This is phosphorence from T1 to S0. So listen, this will come to this and this will come to this. So from singlet S1 row, this is triplet 1. So triplet to S0 will be phosphorus. So listen, delayed phosphorus. What is from ground state S0 to that will go to the S1, higher energy level, lower singlet excitation, and that will radiative permanent transition to triplet. So this will come to triplet. So this is called delayed phosphorus. So these are the different processes occur when a molecule or electron will excite. These are vibrational level and rotational. So you can see this is ground state, singlet ground state as you know. When electron will can jump to this first singlet state S1 and second singlet state S2. So these are the vibrational energy levels, and these are also vibrational. So this is ground state. So if the electron can jump to triplet state, so this is excited triplet. From excited triplets to ground state, this is phosphorescence. So timing is 10 to the power minus 3 second to 1000 second. So you can imagine this after removal of light, it can emit the energy. So listen, it will emit from S1 to T1 intersystem crossing. So here emission is the internal crushing, internal conversion. So you can see from S1 to S0, this is fluorescence. So this is a quenching process. So molecule contains sigma electrons, pi electrons, and non-bonding electrons. The electrons may be present in bonding molecular orbita. It is called as highest occupied molecular orbital HOMO. It has lowest energy and more stable. When the molecules absorb radiant energy from a light source, the bonding electron may be promoted to antibonding molecular orbital. It has more energy. So you can see the process of promotion of electron from HOMO to LUMO. So HOMO is highest occupied molecular orbital. LUMO is the lowest unoccupied. This is LUMO, not LUMO. LUMO, lowest unoccupied molecular orbital absorption energy. So excitation occurs from HOMO to LUMO. So the electron can jump. So if one electron will jump to another state, so the spin can be same, can be different. If the spin will be the same, then this is triplet state. If the spin will be opposite, then that will be known as doublet state. If spin are a state in which all the electrons in a molecular pair, then there is a singlet state. So these are the different situations occur when electron will jump. The light of appropriate wavelength is absorbed molecule electrons to promote from singlet state to excitation. So these processes can be collision, deactivation, fluorescence, and phosphorescence. So what is collision deactivation? In which entire energy is lost due to collision, deactivation, and no radiation emitted. Fluorescence, excited singlet state is highly unstable. Relaxation of electrons from excited singlet to singlet ground state with emission of light. So at favorable condition like low temperature, absence of oxygen, there is a transition from excited single state to triplet state, which is called intersystem process. So these are the different factors which will affect fluorescence intensity. So it is can be concentration, quantum yield of fluorescence, intensity of incident radiation, oxygen, pH, temperature, viscosity, photodecomposition, quencher, scatter, and solvent. So these are the different factors which affect the fluorescence intensity. So concentration. Fluorescence intensity is proportional to concentration by using Beer-Lambert's law. So Beer-Lambert's law is nothing but A absorption is epsilon C. So absorption depends upon the concentration of solution and path length. So here I is the transmitted light of intensity. I0 is the intensity of light intensity. C is the concentration, A is the path length, epsilon is a molar extinction coefficient. So quantum yield of fluorescence, number of photons emitted, and number of photons absorbed. The quantum yield always will be less than 1.3. Since some energy is lost by radiation of less pathways, collision, interstitial pulsing, and violation less. So quantum yield is nothing but number of photons emitted by number of photons observed is always will be less than 1. Since some energy is lost by radiation of less perfect color. So whatever the intensity of incident light, increasing intensity of incident light on the sample of fluorescence will increase the instrumentation. So source of light, filter and monochromators, sample cells, detectors. So instrument, the most common type of instrument is single beam fluorimeter, double beam fluorimeter, spectroscopic. So these are common instruments used in fluorimetry and phosphorimetry. So what about the phosphorimetry? Spectrophoto spectrophosphorimeter is similar to spectrophotometer, except that the former instrument must be filtered with a rotating shutter device commonly called as phosphorus, a sample system which maintained and decode nitrogen temperature. So photoluminescence structure. The presence of benzene ring and the nature of substituent on it seem to favor the fluorescence behavior of the molecule. Halogen substituents tend to decrease in fluorescence and shift to fluorescence bands when longer on the effect increase. So this is photoluminescence structure. So you can see this is known as fluorescent and phenolphthalein. So these are known as photoluminescence. Compounds with fused ring are found to be especially fluorescent, and the extent of fluorescence is found to be directly proportional to number of rings in the molecule. So this structure can be used as photoluminescence. So you can use a biphenyl, chlorine, and a 8-hydroxyquinoline complex with a zinc. The fluorescence observed with rigid cyclic molecules with pi bond is found to be enhanced by electron donating groups NH2 wires. The electron withdrawing groups such as COH, NO2, N double bond N, Bri, CH2Cl tend to reduce. On the other hand, non-rigid molecules do not fluoresce such as rapidly withdrawal. So you can see these are the molecules: pyridine, quinoline, isoquinoline. Any side carbon compounds, heterocyclic compounds, can be used as fluorescents. As regards fluorescence, it has been observed that introduction of certain paramagnetic metallics such as copper, nickel give rise to fluorescence. These ions do not induce fluorescence; on the contrary, magnesium zinc compounds show strong fluorescence. Phosphorus is affected by the longer structure, such as unsubstituted cyclic and polycyclic hydrocarbons. So, introduction of a nitro in a structure dimensions, intensity of fluorescence diagram. So, this is all about fluorimetry. We can see from the initial side. So, this is where what is fluorimetry, what is. So, you can see what is fluorimetry. that phosphorates. So photoluminescence two types, fluorescence and phosphorescence. What is fluorescence? So emission of light is known as fluorescence. When certain light is incident on a substance, the substance is known as fluorescent substance. The timing is 10 to the minus 8, 10 to 10 minus 8 seconds. So even after light is cut off, the phosphorescent substance can be. In a phosphorescence process, the electron did not change in speed. So large substance known which can absorb UV visible light. Fluorescence is the emission of visible light by substance that has absorbed light with different photoluminescence. So what is chemiluminescence? Chemiluminescence is another phenomenon that falls in the category of luminescence. This refers to this refers to emission of radiation during a chemical reaction. So you can see here. So this is nothing but Jablon's diagram. So here S0 to S1, S2, T1, etc. So this transition are known as phosphorates and fluorescence from T1 to S0 phosphorates, from S1 to S0 fluorescence. Principle, this is the excitation of HOMO-LUMO interaction. So excited electron will jump from HOMO to LUMO. So during this process, we will have a ground state sunlight and excited state can be triplet or duplet doublet. So during this process, we will see fluorescence and phosphorescence. So these are the different factors which will affect fluorescence intensity. The Beer's number law as concentration required for the absorption. Quantum revealed the number of photons emitted by number of photons emitted. So instrument source of light, these are the instrumentation. So instruments size single beam, double beam, type and spectrophotometry. So what is phosphorimeter? So this is nothing but a spectrophotometer. Photoluminescence. These are the two examples of photoluminescence. So this molecule can be used for photoluminescence. So now So, as the name refers, or name justifies, is the spectroscopic technique used for determination of molecular mass. So, we get a molecular peak, which will be the molecular mass of the system. What is mass spectroscopy? Mass spectrometry is an instrumental technique in which sample is converted to rapidly moving positive ions. What will convert? That will convert to rapidly moving positive ions. Okay? By electron bombardment and charged particles are separated according to their masses. What is mass spectrum? Mass spectrum is a plot of relative abundance against mass and charge ratio. So, mass spectrum is nothing but a plot of relative abundance कितना compound है against the ratio of charge by mass by charge E by M by E ratio. So relative abundance versus mass by charge. So what is mass spectrometry? Mass spectrometry is an instrumental technique in which sample is converted to rapidly moving positive ions by electron bombardment. So it's a mass spectrometry principles. So mass spectrometry allows us to determine the molecular mass and molecular formula of a compound, as well as a certain structural features of compound. In mass spectrometry, a small sample of compound is introduced in an instrument called mass spectrometer, where it is vaporized into vaporized and ionized as a result of electrons being removed from the molecule. So ionization can be accompanied by several ways. The most common method of bombardment of vaporized molecules with beam of high energy electrons. The energy of electrons beam can be varied, but a beam of about 70 electron volt is commonly used. When the electron beam hits a molecule, it knocks out an electron, producing a molecular ion, which is radical cation species with unpaired electron and a positive charge. So a molecule, when an electron beam bombarded, so molecular ion radical cation will form, and one electron will remove. So what is the process? When an electron beam hits a molecule, it knocks out an electron. One electron will remove from the system, produce a molecular ion that is known as a radical cation, a species with unpaired electron and a positive charge. So this is most common method of bombardment of this one. So here mass spectrometry, a small sample of compound will be used. So M is the molecule. If electron beam will bombard, so we get a molecular ion or radical cation here with one electron. So first, what is the basic principle? What are the steps? Organic molecules are bombarded with electrons. So it will bombard with electrons. So organic molecule will bombard with electrons. So it will convert into highly energetic positive charged ions. So that will be known as molecular ion. Further, it will break off into smaller ions. So that ions will be known as fragment ions or daughter ions. And the foreign ions are separated by deflection in magnetic field according to their mass and charge. And this will be result the mass. So this is the flow chart of whole the process of mass spectrometry. So first what will happen? Organic molecule are this will convert will be converted into a molecular radical molecular ion. This will convert into highly energetic positive charge. That can be molecular ion, that can be parental. Further, this will break into different smaller tracks or fragments or deuterions. So the four ions separated by deflection in magnetic field according to their mass. So first organic molecule will bombarded by electrons and this will convert into a positive charge cation which has more energy and further they will break into smaller ions which is a fragment ions and by using the deflection of magnetic field this will separated by mass by charge ratio will get the mass field. So you can see here. So this is a molecule. This will bombard with a light, and one electron will remove or molecule will become a radical cation. So this radical cation has high energy. So that can be cation, that can be radical, that can be neutral molecules, that can be molecule, can become cation, can become radicals, can become neutral molecules, or can become radial cations. So this is the whole instrument of mass spectroscopy. You can see it's very complicated machine. So this is a neutral molecule sample when the electron beam will pass. So positive charge particle generate here. So listen here electron beam will give. This is filament is given. So negatively charged isolated and focusing plates are there. So vacuum pump is there. Neutral molecules, neutral fragments and negative ions will come to this. These are the magnet ones attached to this pipe and analyzer tube. So positively charged ions reflected according to mass by charge. So ion exits it and it will collect and will record or will record. So this is the whole process of mass. So a beam of high energy neutron causes molecule to ionize and fragment. So positively charged fragments pass through the analyzer. So you can see through this instrument, through this instrument we'll see. Hello. So is it visible now? Hello? Respond anyone? Is it visible? Hello? Hello? Sucheta, is it visible?
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay. So you can see this is the total instrumentation of mass spectrometer. So sample will be inserted here, neutral molecule. So due to presence of electron beam, the positive charge will form here, and here we have different plates. So magnet is given here. So the fragments will reflected in different directions, and that will be collected by the recorder. So this is the complicated process present in this spectrometer, mass spectrometer. This is the whole process. So what we'll get in the mass spectrum? Okay, so we'll get different types of peaks. So let us discuss what are the peaks we'll get in mass spectrometer. So first peak we get molecular ion. So we'll discuss what is molecular ion, then fragment ion peak, rearrangement ion peak, metastable ion peak, multi-charge ion peak, base peak, and negative ion. So we'll get different peaks. So I'll take 2 minutes break. Just. So we are talking about different peaks. So what is molecular ion peak? So listen, when a sample is bombarded with electrons of volt 9 to 15 electron volt, so due to loss of one single electron, we'll get M plus, the molecular ion peak. So we'll get a positive charge or cation of a molecular mass. So fragment ion peak. Suppose we have given a methane. So methane has how many? 12 carbon. This is for 16. So 16 mass peak we get. That is molecular ion. When an energy is given further more up to 70 electron volt, so this will fragment into atoms of lower mass. Then rearrangement ion peak. Recombination of fragment ion is known as rearrangement. So what is metastable ion peak? The ions resulting from the decomposition between the source region and magnetic analyzer as called metastable ion. This appear as a broad peak called metastable ion. The ions resulting from the decomposition Relation between the source region and magnetic analyzer are called metal. Atoms may exist with two to three charges instead of due to a single charge. The peaks due to this charge ions is known multi-charge ions. So base peak. So what is base peak? The largest peak in the mass spectrum corresponding to most abundant ion, most intense peak is the spectrum depth. So base peak is the most intense peak. So largest peak is the base peak. Negative ion peak. Negative ion are formed from the electron bombardment of some. These results due to capture of electrons by a molecule during. So you can see. So these are the different fragments, and this is the base peak. So base peak can be molecular ion. Here this is the base peak, and here is the molecular ion. So base peak is the most stable peak or most abundant peak. So these are the different peaks we will observe in the mass spectrum. So you can see fragmentation of molecular ion produce only one. So we have a molecular ion. So this will after when a electron beam fall upon this, so that will converted into radical cation. So this can be fragment into A radical and B plus cation or A cation B radical. So let's say molecular ion being molecular weight of a compound. So molecule, let's this molecular weight electron beam. So we get a radical. So base peak is the peak with greater intensity, and this will be the highest peak due to its having the greatest relative abundance. The base peak is assigned as a relatively intensity of 100%, and the relative intensity of each of other peaks is reported as a percentage of base peak. Mass spectra can be shown either as a bar graphs of tabular form. So base peak is the most intense peak, most large, highest peak in the mass spectrum. The way a molecular ion fragments depends on the strength of the bonds and stability of fragments. So this mass spectrometer records a mass spectrum. So you can see this is a mass spectrum is given as a sample. So mass spectrometer records mass spectrum, a graph of the relative abundance. So you can see this is the relative abundance x y-axis, in x-axis mass by charge ratio. So this is the graph versus relative abundance versus mass by charge ratio. So listen, this highest peak is the base peak, and these are fragment peaks. So this peak is molecular ion peak. Uh, So here you can see mass by charge ratio, different mass by charge ratio. So you will observe 43 in case of 43 molecular ion, 100% abundance. So here what will the 43? This is the 43. So let's just discuss the mass spectrum of N-pen. If you look at this pentane molecule in presence of electron beam, that will convert it into a radical cation. What is the mass by charge ratio? 72. So you get a molecular ion at 72. We are getting total molecular mass of a compound. Then this 72 can be fragmented in different fragmentation. So here one fragment, here one, here. So what is the mass by charge? 43. So we get a peak at 43. So we have a mass by charge 29. So we get 29 here. So we have a mass 57. We'll get a peak at 57 also. So we have a mass by charge. So positive charge we get the mass of the fragment atoms. So if you look at this 43, one H plus will remain, we get mass of the photon. This is the allyl cation. So we get one peak at 41. You look at the first 72 molecule. So mass by charge 57. So this is for isopentane. So in case of isopentane, we get the mass spectrum like this. So here again this 43 will be metastable. So this is the N-pentane, this is the isopentane. So these are comparative of mass spectrometry. So isotope M plus 1. So if a molecule will contain the atoms or elements which have isotopes. So in this case, we'll get two peaks, one peak single mass, another will be mass plus one or mass plus two. So what are the isotopes? Carbon 12 and 13, 13, hydrogen 1, 2, nitrogen and 15, oxygen 16. So these so sulfur, chlorine, chlorine, etc. So these are the different abundance and their percentage. So if you look at the relative amount of acetate, M plus 1 is to 1 number of carbon. So these are the calculation of M plus 1 and M plus 2 amount. So we look at only where we get this M plus 1 and M plus 2 acetate. So you can calculate in case of carbon. So in case of chlorine, you can see M plus 2 peak 3 is to 1 chlorine, M plus 2 peak 1 is to 8 chlorine. For chlorine, we will get 3 is to 1. For bromine, we will get 1 is to 1. So, to determine the molecular mass or molecular formula, high resolution mass spectroscopy requires. So all the mass spectra shown in text were determined with low resolution mass spectrometer. The spectrometer gives nominal molecular mass of a fragment to mass to nearest whole number. High resolution mass spectroscope can be determined exact molecular mass. So you can see molecular mass of this molecule 122.10. So exact mass can be detected by mass spectrometer. So you can see of different isotopes of hydrogen, carbon and their molecular mass. So rules for fragmentation. So when we are fragmenting different molecules, so there are some rules. So the relative height of molecular entity is greater than straight chain compounds and decreases the degree of branching. So these are the relative height of molecular peak usually decrease with the increase. So these are the different these are the different rules of fragmentation depending upon the stability of cation and anion. So we have a rules for double bond. So saturated ring can be one. So here I'm typing. Sorry, here I'm searching, looking for this one. Mac laptop again. Just a minute. So listen. Oh, yeah, that one. So these are the different rules for getting fragments. You can see on the slide. Also depending on pattern and double ones, suppose double ones will be there. So we'll get a allyl cation, which one is more stable. For a cyclic compound, also we get a Diels-Alder reaction. Also, this alkyl group will be more. So we'll see this. So this is very very. So listen. So during the fragmentation of molecule, one rearrangement is known as McLafferty rearrangement. So this rearrangement used during the fragmentation of a molecule. So this will rearrange if we have a alpha, beta, gamma hydrogen. So due to the presence of gamma hydrogen, we get a molecule like this. So this is rearrangement of ions or fragments whose origin cannot be discussed. So, but due to intramolecular atomic rearrangement, rearrangement involving migration of hydrogen atom molecules that contain a heteroatom. So we'll get this compound. So to understand macro rearrangement, a molecule must possess an appropriate located heteroatom. Okay? So this is due to macro rearrangement. So we get this molecule, and this will be the most basic M by Z ratio 58. So this mass we will get by using macrolapid. This gamma hydrogen will come here, and this bond will come here. This one, so we'll get alkene here, and we'll get intermediate. So this cation has more abundance in the surface. So you can see due to McLapper rearrangement, we get this 106 as a base pair. Okay, so this is the naphthalene. So we can see, let's just see some mass spectrum of different compounds. So this is naphthalene. So this is cyclohexane mass peak. So this is the peak of medicine, a compound like this. So this is alkyl halide. So you can see in the alkyl halide you get 41, 43, M plus 2. So this is a mass of 2 chloropropane. Mass of secondary butyls. MS of ethyl, the secondary butyl ether. So these are the different mass spectrum. You can see different isomers of them. So mass spectrum will look like this. So this is the plot between relative abundance versus mass by charge. So you can see this. So this is the mass spectrum of ethyl phenol, luminal and natural product. So these are the different mass spectra. So we'll go to the another part remain here. So the difference is not there. Okay, we go to the another absorption. Okay, this one. So what is atomic absorption and emission spectroscopy? So last part of this. So atomic absorption spectroscopy. So you can see atomic absorption spectroscopy is a very common technique for detecting the metals or metallos. So listen, this is used to detect which atoms or elements are present, which metal, which metals or metalloids are present. So it is very reliable and simple to use. It can analyze over 62 elements. So in a molecule contain what are the elements, what are the atoms, in which percentage. So this atomic absorption spectroscopy will tell which metals or metalloids are present in which percentage. So it also measures the concentration of metals in the sample. So you can see this is the first atomic absorption spectroscopy in 1954. The first atomic absorption spectrometer was built by CSIR scientist Alan Wallace in 1954. Incoming call from subject has been identified by your caller. Okay, just a minute. Hello? Huh? Uh, पठेल पठेल. So elements detectable by atomic absorption are highlighted in the. So these are the elements can be detected by atomic absorption. The same hydrogen, helium cannot detect. So in the pink color, that can be detected in atomic absorption. Lithium, beryllium, magnesium, sodium, scandium, iron, boron, etc. So in the periodic table, the elements in pink color can be detected by atomic absorption spectroscopy. So the technique uses basically the principle that three atoms generated in a atomizer can absorb radiation at specific frequencies. Atomic absorption spectroscopy quantifies the absorption and ground state atoms in the gaseous state. The atoms absorb ultraviolet and visible light transition to higher electronic energy levels to analyze concentration. So this is a technique used spectrometer, a hollow cathode schematic diagram of atomic absorption spectroscopy. Hello, is it visible?
Yes, sir.
So, atomic absorption spectroscopy can be used in environmental study, in food industry, in pharmaceutical. So, what is the metal percentage of metals present in field industry? Suppose in a Maggie, what is the percentage of lead we can measure by using atomic absorption spectroscopy? So, listen, another spectroscopic technique is atomic emissions. So we are talking about just now we have talked about the atomic absorptions. Now we talk about atomic emissions. So the atomic absorption is a very common technique to detect the metal. So you can recap this. So this is the history of atomic absorption spectroscopy. So these are elements are detectable for atomic absorption spectroscopy. Principle of atomic absorption spectroscopy, concentration measurement. So this is atomic absorption spectrometer instrumentation. So this is nothing but atomic absorption spectroscopy. Spectrum. This is the schematic diagram of atomic absorption spectrum. So these are the applications of atomic absorption. Now we go to the atomic emissions. So in that case, one will atom will be absorbed here emission. So hollow cathode lamp will be there, one flame will be there. So the sample will be go through this one. So we'll get the emissions. So atomic emission spectroscopy is a method of chemical analysis that use the intensity of light emitted from a flame, plasma, arc, spark at a particular wavelength to determine the quantity of an element in a sample. The wavelength of atomic spectral light gives the identity of element, while intensity of emitted light is proportional to it. The principle of atomic emission spectroscopy is that atoms are thermally excited to higher electronic energy levels, then relax back to lower electronic energy levels by emitting radiation in UV visible rays. So emitted radiation is detected and used to determine which elements are present and their concentration. So flame photometry is the simplest technique in absorption emission spectroscopy, having the advantage of cheapness, simplicity. It is applicable to solution only. The elements are easily ionized, therefore only require a low temperature. So in flame photometry, the clinical laboratory will determine sodium, potassium, lithium. So a sample solution can be run by a nebulizer. So this is total about flame. The advantage of flame photometry are the low cost, being considered cheaper than any other absorption spectroscopy or emission spectrum. So this is the flow chart of a schematic diagram of atomic emissions. Okay, so this is all about our atomic absorption. So you can see the atomic absorption spectrum. This is all about. So if you look at the already we have covered all of them. So one thing I'll show you just and that's actually in your link of material, this spectroscopy is not given. That's it. Okay. So you can see separation spectroscopic methods. So we have already discussed all of them, almost all, ion, size, membrane, UV, IR, colorimetry, phosphometry, atomic emission spectroscopy, three-dimensional mass spectroscopy, and etc. Only I'll show you some hydrogen. You know hydrogen spectroscopy. So I'll say in a small proton NMR. So you can see I'll show you only the spectrum. So you can see. So this is NMR high proton NMR spectrum NMR instrument. So NMR instrument is nuclear magnetic resonance. So NMR here radio waves used as electromagnetic radiation. So in NMR we this is the NMR key where we use the spectrum here. So this is the instrument of NMR. So this is the NMR tube. So we'll see some NMR spectra. Just a minute. Yes. So these are the theory. So we are not talking about this. Just a minute. So this is the instrumentation of NMR instrumentation. Sample holder, radio frequency transmitter, magnetic coils, etc. You can see this example table it a clear. So now see in concept of cell ingredient, this cell ingredient already belong in your PS classes of field of it. So these are the different factors. Now see some spectra here. So this is the NMR spectra. You can see here. So here this is two doublet, singlet and triplet. Splitting up total we can see. So here we calculate the different chemical environments. So so you see the spectra here. So this is the splitting rule. So these are the different animals. So almost all. So in the 4 days, I think today is my last class. So we have wind up almost all the units. So it is difficult to cover all the units in one. Okay. Anyhow, we have it. So
Thank you, sir.